Hello everybody, my name's Noel. I'm making this YouTube video to explain to physicists, nuclear physicists, maybe nuclear explorers, whoever might be interested, about how the numerical interrelationship patterns within the isotropic vector matrix are identical to those which exist within the nucleus of the atom. What began my interesting investigations was studying books like Synergetics by Buckminster Fuller. The science of synergetics was introduced in 1975, and the second book there, Synergetics In, was released a few years later. They're basically one large volume. In it, he pointed out, among many other things, about how when you closest pack unit radius spheres, you create a new metric or a system of measurement called the isotropic vector matrix. And this is a 6-axis system. I'll show you some models about that in a second. But the point is that when you closest pack unit radius spheres, you can closest pack 12 around 1 in order to form what's called the vector equilibrium or the cubooctahedron. When you put another layer of closest pack spheres around that, you come to 42, and the next layer puts 92 on those. And he hypothesized by calculating the numbers of closest packed spheres in the vector equilibrium that in the first 3 shell layers there's 146, equaling the total number of neutrons in uranium. You add a 92 icosahedral layer of protons, and you get the atomic mass of the uranium, 238. He did the same thing for the neutrons. 12 on the first layer and 42 on the second of that vector equilibrium. You add a 42 layered icosahedron, and you get 96 molybdenum. 2 protons and 2 neutrons, you get magnesium. So this led me to investigate further along some different lines. I'm going to go ahead and erase this, and I'm going to move on over and show some models and explain just a little bit about synergetics. Bucky originally called synergetics energetic vectorial geometry. He started studying how energetic patterns or energetic vectors will self-stabilize themselves into intertriangulated patterns, and then these self-stabilizing intertriangulated energy patterns would then build themselves up into polyhedral forms, creating larger and larger polyhedrons. So when you closest pack unit radius spheres and you pack 12 around 1, you create, as I mentioned before, what's called the isotropic vector matrix. The 6 axes connect the 12 vertexes of this system. So this is a different metric than what we're currently using as the XYZ Cartesian coordinate system. If you're not familiar with that, really basically, because one other people don't, you got the X, the Y, and the Z Cartesian coordinate systems. And it's thereby that all mathematical endeavoring has been done there for in all science and math. So when Bucky uses a system and he comes up with interesting numerical interrelationship patterns just revolving around the neutron and proton count of these various elements, I say to myself, I'm going to investigate a little bit further. So I drew up these charts to see how many of these interconnections exist when these polyhedrons get really big. So any kissing point between these closest packed spheres is a place where the energy can change from one sphere to the next. We're calling this an energy vector. It's a kissing point. It's a vector point where energy transmits itself one way or another. Energy that has mass and a velocity is going in a certain direction. Self-stabilizing itself once again in polyhedral forms, which create bigger and bigger polyhedral continuums. Bucky showed some interesting models wherein he was helping to model some of the different behaviors that physicists were finding. For instance, he got an annihilation and conservation model by understanding Boltzmann's theories then of energy conservation and annihilation. I just made this little model that will slip phase the octahedrons 4 volumes compared to the volume of the tetrahedron as 1 into 3 volumes and 3 tetrahedrons just by shifting this vector 90 degrees. You lose one of the quantum modules or volumes and you end up with 3 volumes within that tetrahedral model. Shifting it back again gains a quantum of energy or a volume of energy from somewhere in the universe. I'm not going to explain too much about synergetics, but I do want you to understand then this is the external field or vector set of this model here. You'll notice the same 6 square faces and 8 triangular faces. What Bucky understood was that squares and pentagons and hexagons, like this square here, are not structurally stable. See how they move in and out? Only triangles. This, to digress, this whole model just sticks in rubber bands. So it's all rubber band tensors. Only triangles hold their structural stability. So we built this model. It's called the jitterbug transformation model. It shows how then the transformation from the vector equilibrium, how cute, huh? Down to the octahedron and back again is a jitterbug model showing energy and shape transform themselves. Here's an icosahedral stage right here. If you were to add 6 vectors to the 6 squares, it would stabilize this into the icosahedral frame. From here, it'll also spin shift down. You can shift it up into the tetrahedron. It's a very interesting model and kind of fun to play with. I'm going to show you something else just real quick, how the octahedron transforms into the tetrahedron with this model. By shifting its 2 phases down that way into and out of an octahedron and a tetrahedron. Back and forth shift phasing. So these are just interesting models which show how shape transforms itself. We don't really see that when we use the XYT Cartesian coordinate system because what we're doing is we're using an unstructured system. When we move to a stable system using a stable metric, or once again a measurement system, based on the XYZ Cartesian, based on the 6 axes of the isotropic vector matrix, we find some very interesting numerical interrelationship patterns with those vector totals when we get to very, very big polyhedrons. I drew up these charts to investigate further the numerical interrelationship patterns between these polyhedron when they get to very high frequency. So what I did then was I drew these all out, and I was going to draw them out farther if needed, but there's a big mystery in science regarding the amount of angular momentum during the coupling process. It relates to the fine structure constant, which is 1/137, or approximately thereof. In the reflexive universe, Arthur Young talks about, just basically, how the nuclear particles, the electron and the proton, created by photons, are the first occurrence of permanent mass and charge. This is the basic substance of the universe, as compared with the activity of the light that created them. But not all of this activity, or more correctly, angular momentum, is condensed into mass. For reasons which are still unknown, 1/137th of the angular momentum remains uncommitted and free. This 1/137th is known as the fine structure constant. It is this freedom which manifests itself in the uncertainty of position and momentum that characterizes the fundamental particles. On page 58, he goes on to explain a little bit further then about how what's important for the present theory is that in order for an electron to change orbits, the shape of the orbit has to change, and shape is due to angular momentum and not to energy. So there's a mystery about this amount of angular momentum which is lost or conserved or remains free. And so when I drew up these charts just to explain then, if you want to take a quick look closer here with me, Christian, what I did basically, I just started with the natural numbers, 1 up to 144. What happens then is, kind of if you put 1 sphere next to 2 spheres, you get a triangle. Put that next to 3 spheres, you get a bigger triangle. 4 spheres gets you a bigger triangle, etc. You get bigger and bigger triangles. These triangular numbers are associated here then. You got 3 in the first triangle, 6 in the second triangle, 10, 15, 21, etc. So I've drawn those out. when you put this first sphere on top of the three spheres, you create a tetrahedron. This is your first insideness and outsideness in the universe is your tetrahedron. So this polyhedron then has 4 vertexes, or 4 closest packed unit radius spheres. When you take those 4 spheres, you place them up on top of the 6 spheres of the triangle, you create 10 total spheres for the next size next size tetrahedron. It's herein that you begin truncating the tetrahedron to create the other polyhedrons. All the other polyhedrons I'm discussing then in my book are truncated from this original tetrahedron as it gets bigger and bigger and bigger. Every second frequency you truncate the vertexes and you come up with the octahedron. The octahedron has 6 vertexes or 6 closest packed unit radius spheres. The next level, you've got 20 spheres closest packed in that tetrahedron, and then the next level you've got 35. When you truncate those 35, you truncate 16 and you have 19 left over for that next size of octahedron. You truncate the octahedron, 6 vertexes, and you get 13 total closest packed unit radius spheres in the first frequency of the vector equilibrium. On every 6th frequency of tetrahedral development, you can truncate it so that you get the cube and the tetrachydecahedron. Cube has 14 spheres, tetrachydecahedron has 38. This model up here is the 6th frequency cube. I've colored all of the balls so that one can see the truncation process, truncating the tetrahedron's top 10 balls, corner 10 balls, corner 10 balls, and then you get the octahedron with this yellow. Truncate the octahedron and you get the tetrachydecahedron. Truncate the tetrachydecahedron and you get the cube. Every 12th frequency of tetrahedral development, the vector equilibrium and the cube and the tetrachydecahedron and the truncated tetrahedron all show up in the same measure marker. This happens every 12th frequency. It's a very interesting phenomena. So what happens then when you get to these super high frequencies, and we're not even that high yet, when you get to the 137th frequency measure marker, some interesting phenomena occur. You have a certain total number of spheres connected to each other, and you have a certain number of kissing points or vectors, which are connecting all of those closest packed spheres. You also have a volumetric containment field inside of that. So frequency in synergetics is a measure of the edge length of the polyhedral system. The edge length can be measured by the number of intervals between closest packed unit radius spheres. So this would be called a 6 frequency tetrahedron because it has these 6 vector connections or 6 kissing points, 6 intervals between that edge length. This, for instance, is a 2 frequency cube. This is a 4 frequency tetrahedron. This is a 1 frequency tetrachydecahedron. This is a 4 frequency octahedron. 1, 2, 3 frequency vector equilibrium, a 3 frequency icosahedron, and that's a carbon-60 molecule. There's 60, and that's a Buckminster Fuller ring, just a model of it. What's interesting while I'm looking at this real quick is 92 spheres on the external of the icosahedron, 92 on the external frame of the vector equilibrium. It's simply a shift. I'm going to just keep that point in there, Christian. It's a shift that turns these square faces to the triangular faces when the internal balls are removed. This jitterbugs, as I showed in this model, down to this shape. So that's what frequency is. Now, what's interesting about frequency is that in synergetics, as Bucky says, I'm quoting here, in section 9062.10, synergetics accommodates the direct expression of both angular and linear accelerations of physical universe. The frequency of the synergetics coordinate system, synchrosystem, simultaneously and directly expresses both angular and linear accelerations of nature. Fuller goes on to explain that when any point or polyhedron expands omnidirectionally, the frequency of the system relates the radial measure from the center of volume of the system to the circumference to the linear accelerations of the system, and the circumferential measure around the system to the angular accelerations of the system. Now, in section 986.112, he says, Vectors always represent energy forces of given magnitude operating at given angles upon given entities at given loci. Vectors do not occur singly. They occur only as the family of forces interacting in any given physical circumstance. Now, when we count the total number of vectors in synergetic structurally stabilized polyhedrons, we see a family of energy forces which relate identically to the forces within the nucleus of the atom. So, angular accelerations in the universe, or angular momentum, then are related to the frequency of the synergetic system. If you take away 1/137th of the system measurement, when you get to this large polyhedron, you get the 136 frequency. What's interesting then in this 136 frequency is you get octahedrons and vector equilibriums with really interesting total number of vector counts. For instance, the total number of vectors in the octahedron at the heart of the tetrahedron, which is a 136 frequency, has exactly 9,384 vectors times 137 vectors. Now, scientists are probably well aware that 938.4 is the mega electron voltage of the proton, and 137 is the inverse of the alpha measure, or the fine structure constant. Now, the vector equilibrium has an interesting number of vectors. It has 800,088. Bucky always said when the universe shows us some interesting numbers, we should pay attention. And so what's interesting about this numbers is this equals 9,384, which is a proton's mega electron value basically, times 6.625, which is Planck's constant, times 10 to the 34 or whatnot. And you add that to 9384, 000, divided by the number of the number of naturally regenerative chemical elements. I know that could be debatable, but 92 of them. Times that by, once again, Planck's constant. Now that's strange, isn't it? That you bust up this tetrahedron, you got a vector equilibrium with it, and it's got 9,384 times 6.625 vectors plus 9,384,000 divided by 92 times 6.625. I went ahead and investigated further. So before I go on to higher frequency measures in the tetrahedron and the other polyhedrons and what their vector totals are, I want to explain a little bit about just what I had done. I drew up these other charts after I had drawn up the initial chart. The initial chart, once again, shows the total number of vectors, which is kissing points between the closest packed spheres, as well as all those closest packed spheres, and these various polyhedrons, as well as the amount of tetrahedral volume. Since I didn't explain it before, I'm going to explain real quickly how synergetics is very interesting, because it shows how we get second and third powering in ways that are not squaring and cubing. Right now we say a 2 inches on the length of a square by 2 inches on the length of a square equals 4 square inches. If you turn that into a cube, you say there's 2 inches on the height, so you say 2 times 2 times 2, bringing it to 8 cubic inches of volume or whatnot. If you use the tetrahedron as the base unit of measurement, you also, with triangles and tetrahedrons, get second and third powering accumulations of facial area and volumetric space. And so this is interesting because it shows that nature has other means of second powering and third powering other than squaring and cubing. So when we verbalize something squared or something cubed, we're really doing it erroneously when we consider that it's also triangling and tetrahedroning, which means that we might not know exactly what it's doing when it's phasing into these larger systems. If you'll take a close look then, this first tetrahedron with one triangular face has 1 to the second power, total number of triangular space. Go to the next one, you have 1, 2, 3, 4, total triangular space for 2 to the second power number of triangles. Go down one further and you have plus the 4, 5, 6, 7, 8, 9. So 3 to the second power. This continues ad infinitum. You'll count the volumes also. One volume of tetrahedron with an edge length has 4 volume when it's an octahedron of the same edge length. You'll notice that this is an octahedral tetrahedral trussing matrix. Tetrahedrons and octahedrons packed together enclose all space. Counting them then, you've got 1 volume, or 1 to the 3rd power. When you've got 2 edge length, you've got 1 volume here, 1 volume in this tetrahedron, 1 volume in this tetrahedron, 1 volume in this tetrahedron, and there's an octahedron at its center with 4, for a total of 8. So 2 to the 3rd power is 8 tetrahedral volumes. Go to the next one, and you'll count up for a total of 27. To the next, a total of 64. To the next, a total of 125, and then 216 for a 3rd powering progression. So we'll notice that we had triangular and tetrahedral accounting, which 2nd and 3rd powers in the same way that the cube 2nd and 3rd powers. But what we'll notice that when we use the edge length of the cube and we relate the other polyhedrons, volumetric measure, we have an irrational volumetric domain set up. When you have 1 foot edge length on the cube, you got 1 cubic foot of volume. When you got 2 foot edge length on that cube, you got 8 cubic foot of volume. On the tetrahedron, when you have 1 foot on the edge length, then you have 0.11785 cubic feet. On the octahedron, with that same 1 foot edge length, 0.4714. Vector equilibrium, 2.3574, and that tech chi with that same 1 foot edge length is going to hold 11.313 cubic feet. So when you measure cubically, you go up to the next ones, the 8 cubic, etc. It's always irrational. So what happens then is when you use the tetrahedron as a volume of 1 in our little system of measurement, you get a 4 volume cube because it's 4 times its size. Octahedron, a 4 volume octahedron, which shows up in that 2nd frequency after you truncate it, that 2nd frequency at tetrahedron. You end up with 24 volume in your first cube. And the cube is not measured by its edge length other than saying that's its frequency. What's interesting is that the cube, I'm going to move over to this little model right here. Thanks, buddy. Careful. The cube then, when it's structured and when it becomes an element of the truncation or fractionation of the 6 frequency tetrahedron, as you can see it inside this domain, these 3 red vertexes or spheres and that 1 red one at the bottom are the same as these 4 on this tetrahedron. Lift this up. It's going to break. But anyways, if you lift that up, it has to be lifted up, and then you'll see these tetrahedron. Inside, there's 1 blue one there, 1 blue one there, 1 blue one in there, and 1 blue one there. So the square's, the cube's tilted inside that axis. And when it's first created then as a structured element in universe, it's got 1 volume, 2, 3, 4, plus those 4 for 8, plus 1, 2, 3, 4 more for 12. And then it's also got these 1 volumes at the edge length for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for a total of 24 volume once it's structured. When it gets to the 2nd size, which is in the 12 frequency tetrahedron, it has 63 total spheres. And so in that 2nd frequency cube, you got 2 to the 3rd power times 24, 192 tetrahedral volume. So what you do when you use the 6-axis metric and you use the edge length of the regular tetrahedron as a base unit of measurement, you set up a rational volumetric domain as opposed to that irrational volumetric domain which is set up with the edge length of the cube. So what happens when you set up a rational involvement domain like this, and you understand that you're truncating that tetrahedron every certain number of frequency in order to get these various polyhedrons, every single one of these polyhedrons has an exact number of spheres, closest packed, it has an exact number of kissing points or vectors between those closest packed spheres, and it's enclosing a whole volumetric measurement. So there's never no 0.12784s or anything like that when we're breaking these polyhedron up and measuring them. What I did then was I reduced all of these total numbers to their factors. So what I noticed after that, after I ran up, what are the totals? Broken down to their prime number factors. I noticed that the prime numbers ran in patterned measures. Very, very interesting. So the 7, for instance, will show up every certain number of times within each of the polyhedron's development. So you'll know exactly when it's going to show up again, because the pattern stays constant forever. And that's on all the prime numbers as they show up in all the polyhedrons we discussed. Now, I also drew something up, a chart showing what's called indig patterns, I-N-D-I-G. Indig patterns, then, I drew up right here. And Christian, if you want to take a close look at those whole charts as you're goofing around, start at the beginning and then come on down or whatnot, you know, just people can get a look at them, they can slow it down later and take a look. So basically then, what's interesting about that is that you do what's called indig patterns, and an indig is basically a number, and that's good enough. Whenever you're done there, we'll draw your attention back up here. An indig is created by taking any number and just adding the numbers together until they're one number against you. 3 plus 2 plus 1 equals 6. 6 would be the indig for this number. 9 plus 5 is 14. 1 plus 4 is 5. 5 would be the indig for this number. 9 plus 6 is 15. Plus 3 is 18. Plus 4 is 22. 2 plus 2 is 4, so 4 would be the indig for this number. So what's interesting is that you take these polyhedrons, no matter how many vectors, no matter how many volume, no matter how many closest packed spheres they have, they all run in a patterned way. For instance, the octahedron's volume patterns as 4, 5, 9, 4, 5, 9, 4, 5, 9, and it goes like that forever. And it's kind of interesting because, and I'm going to digress a little bit just to explain a couple of numbers on that indig chart. 4, 5, 9 continuously, right? Well, there's 4 volume in that first octahedron, and 4, 5, 9 times 4 equals 1836. Well, that's the ratio, compared to 1 volume, of the proton. We get some interesting numbers showing up here. If you take the balls or spheres within the cube as they progress, it's very interesting. They all reduce to 159, 159, 159. You take that 159 and you divide it by its first volume count of 24, and you get 6.625. Planck's constant again. There's some other interesting numerical patterns there, but for now I'm going to go ahead and leave it at that, just explaining what I did in order so I could understand basically how the prime numbers pattern. And what I noticed then was that the 17 and the 23 revolved around the 137. And I said, well, it revolves around the 137 so that it shows up at 136. And the 23 revolved around it also. The 17 and the 23, they revolve around that number 137. When this doubles to 274, right now you're going to notice the 23 shows up on the 138 and the 17 shows up on the 136. That's just the basic math, right? Because they're factors. Multiply that by 8, you're 136. Multiply that by 6, you're 138. So in seeing that the 17 and the 23 revolved around that 137, and as I calculated up, I saw that they got farther and farther apart each time that it doubled. So there's kind of a little law of numbers that I was looking at. 137 times 1 plus 1, is that 138? 137 times 1 minus 1, is that 136? Well, basic math. I'm not trying to be silly. You do it times 2 plus 2 times 2 minus 2, and those miss by 2 the first time. Now they're missing by 4. Do it another time, plus 3 minus 3. Obviously, now they're missing by 6. So these keep missing, and I'm wondering when they're going to hit, right? So I noticed that you keep going on down the line. Now they're missing by 132. Right? They're real far away, these numbers. Now they're missing by 134. Oh, and then they meet up at 9,384. Oh, wait, isn't that the mega electron voltage for the proton? Yeah, that's right. So I call that a 0 point. That's where the point of those two prime numbers that are patterning finally meet up. They're at the 9384 level. I found that interesting. You can break that number up in a bunch of different ways. Proton's kinetic energy is 17 electron volts. As I'd mentioned before, its rest energy is 938.4. If you got the alpha measurement, 0.00729, right, times 10 to the 5th, if I'm in that right in my mind, plus Planck's constant times 2 to the 3rd, which is 53. It equals the free neutron's binding energy, 0.782. Multiply that by the 12 vertexes, and you get 137 to the second power minus 1 divided by 2, which equals 9384. I don't know. It seems kind of basic math, and I think that anybody in physics would at least just maybe put those numbers together, like, here's some basic math. It would just be like, what happens if you take the inverse of that alpha scale and you second power it and you subtract maybe an electron from it and divide by 2, and you get that proton. It's really neat. So I started investigating further, and as I began to investigate further, I recalled what I had learned earlier regarding what happens in the 17 frequency plane of the hexagon and that 17 frequency square plane. When you closest stack squares in a hexagonal plane, you get 919 for a total of 918 around 1. And when you do the same thing in a 17 frequency square, you get 613, or 612 around 1. You've got 6 square planes to the vector equilibrium, and you've got 4 hexagonal planes. See the hexagon inside? 4 hexagonal planes inside. So hexagons come in sets of 4 and squares come in sets of 6. Within the vector equilibrium structure. If energy components are closest packed and utilizing the same central sphere, the square and the hexagon cannot both be using that central sphere because 612 are spinning around 1 and 918 are spinning around 1, and that 1 is the nuclear bar. So if you subtract that nuclear sphere, you have 918 going at one time while the other one's doing 613. And then maybe you got 919 going while the other one's doing it 612. Once again, only one can be using that central ball. I just deduced that in this energy matrix of movement, it makes sense to me that when you've got 1839 times 2, flashing with 1838 times 2, you're averaging 1838.5, the neutron. And when you don't have that sphere, these two are equaling 1836 times 2, which is compared to one of those spheres as an electron, equal to the proton and the neutron's ratio. These numbers interested me. And I wondered, did they pattern around any other numbers? And I saw that 613 and 919 pattern around the number 3,677. And might I add that these are all prime numbers, which had, prompted this investigation as things started looking interesting when I noticed that the prime numbers were running in a patterned way when you broke up the totals of the polyhedrons, vectors, and vertex associations. The vertexes are the closest packed spheres. I want to digress just real quick. You'll notice on the vertex here, you don't have to have a sphere. The vertex is an interconnection point between the vectors and the energy units. The energy units will, just with a little bit of gravity or tension or intercoherence, connect themselves and stay stable once again because they're self-stabilizing intertriangulated patterns. I figured out what the numbers of the total spheres and vectors and volumes were because I deduced these formulas here. I found out later that some other people had deduced some of the sphere formulas, but nobody ever deduced any of the vector or kissing points between these spheres totals. So that's how I deduced all the extremely high frequency numbers I'm going to be talking about in a moment here. So 613 and 919 revolved around 3,677 in a very interesting way. I drew up another chart down here. You can sit down right there. Might be a good spot for you, buddy. And then just kind of, we got enough light. I'm going to put some more light on this if you need, or how's your thing?
That's good.
Is that better?
Yeah, it wouldn't hurt.
Let's get it a little bit later. Not to digress, but I drew up two charts because I noticed that the 17 and the 23 revolve around another number. They revolve around the 919. Just the same as the 17 and the 23 revolve around the 137 and meet up at the 9,384 marker. They revolve around the 919, and then they meet up at the 422,280. So that's where it meets up. Oh, here it is. I'm sorry. So it meets up right there. That's your first 0 point. And then you got a difference here of 1,838. And then that 1838 continues to double. Each next point these meet up. So does 422,280. It just always doubles. And you notice that's 1836 times 92. So the proton times the 92 natural regenerative elements. And then multiply that by the prime volume of the vector equilibrium, which is 2.5. I'm not going to talk about that too much more right now. So what's interesting then is 17 and 23 revolve around that. And this number happens to be 9,384 times 45. Yes, that's interesting. The proton times 45. So the 613 then and the 990 revolve around the 3,677 in the same way. First they miss by 2, then they miss by 4, then they miss by 6, and they just keep on missing until they hook up right here. They're missing by 3,677, and they hook up at 6,760,164. What's really interesting then is that when we get to this next scale, I call the quanta scale, the 3,676 frequency tetrahedrons, total number of vectors, kissing points between all those spheres, is equal to 1838.5, value of the neutron, times 2 to the second power, minus 1 electron, divided by 2, multiplied by that neutron, 1838.5, times 4, which is really crazy because you break these vectors up a different way and they total Planck's constant times 10 to the 40 plus inverse of the alpha measure times 10 to the third minus the proton's value times Planck times 10 to the 37 plus the alpha times 10 to the fifth. Very interesting. Now the nucleoctahedron at its center, if you were to truncate that tetrahedron, you got that octahedron, which is the 1838 frequency. Divide those vectors by 2. So when each of these 0 points or meeting points between the 17 and the 23 occur, for instance at the 9384, each time that number doubles, those numbers meet up again. It's the same thing with the 17 and the 23 around the 919. Every time this Penn scale, what I call the Penn scale, and the other one's a quanta scale, by the way, 422,280 doubles, then doubles again, then doubles again. When it doubles 5 times, you have 6,756,480. That's one of its 0 points. When you take the first 0 point of the quanta scale and you divide it by the fifth 0 point of that Penn scale, you get 0.00054. And that's the electron's atomic mass unit, 0.00054, which equals approximately 1 divided by 1836. Now, as these two numbers continue to double, the difference between them will maintain that same difference, 0.00054, ad infinitum. It's just interesting to me that the universe has set up 2 scales wherein the total number of vector counts within each replicate interesting numerical patterns that show up in the nucleus of the atom, and they show a means by which, as this continues to double and this continues to double, they'll still fractionate themselves by that electron's mass, showing a means by which these 2 scales can transfer 1 electron between themselves. So I'm about wrapping up, but I want to talk a little bit about a couple of other things. It's interesting when you look at the polyhedrons this way because they can transform one into another by some basic mathematical formulas. For instance, if you add f plus 1 to the octahedron's total number of vectors, you come up with the total number of cubes, spheres, or vertexes. And I want to reiterate that those spheres are like a hold and stay station for those vectors, which, as maybe they're spinning around, stabilize themselves into intertriangulated patterns. So you don't actually need a sphere there. It's a hold and stay station. It's the total number of hold and stay stations created by the total number of vectors. So anyways, add f plus 1 to the octahedron's vectors. For instance, add the first frequency is 1 plus 1 to the vectors in the octahedron, and you get the spheres in the cube. Add frequency is 2 plus 1 to the vectors in the octahedron, and you get 63 spheres in the cube. So on ad infinitum. You add the third frequency plus 1, or 4 to 168, and you get 172. So the vectors transform into spheres with basic transformation formulas. The tetrahedron's volume, all of its odd volumes, also can transform into the cube spheres with the interesting, very easy to understand formula. The volume, for instance, 27, plus 1 divided by 2. is equal to 14. 125 plus 1 divided by 2 is 63. 343 plus 1 divided by 2 is 172. And those patterns continue ad infinitum. You can also look at these charts, and if you notice then, because they're all made up of basic frequency to the third power accumulations, you can multiply, add and subtract in order to transform any one of these frequencies into any of the other frequencies. So what we find then when we use simple thought is a mathematical transformation model, which uses simple and complex formulas in order to transform one aspect of one polyhedron into one aspect of another polyhedron. So what was interesting about these transformation models, numerical, is that they give us an understanding maybe of some of the mathematical comprehension between how these different models are transforming, as this one did from the vector equilibrium into the octahedron, then down into the tetrahedron. I only made a partial covering over this vector equilibrium of the rhombic dodecahedron. I want to show how when the vectors of the vector equilibrium spin shift 90 degrees, when they all spin shift 90 degrees, they reach hold and stay stations where the faces used to be. So you turn the 14 faces into 14 spheres with the same total number of external vectors, which is 24, and you create the rhombic dodecahedron with 14 spheres. If you take that rhombic dodecahedron and you push gently, take a look from above with this, no, please get right above it like that. There you go, perfect. Sorry, it's all messed up. I messed something up. So all I'm saying then is you can see that it's superimposed over the vector equilibrium in the isotropic vector matrix. When you don't need to do that anymore. So when you push this down then, the other vertexes come up and these 6 faces go in and you have the cube. So the external 24 vectors of the cube can shift phase 45 degrees down into the rhombic dodecahedron and then shift phase 90 degrees this way to turn into the vector equilibrium. Explaining some different shift phasing which Synergetics didn't discuss, but it's very, very interesting. Now, in these different transformation models, we notice something about the volume of the vector equilibrium compared to the volume of the cube, which rests at its center. Remember, every 12th frequency of tetrahedral development, the vector equilibrium and the cube both show up. You take the vector equilibrium's volume, and you take the cube's volume, and you divide them, and you get 2.8125, which is the same as Planck's constant, 6.625, minus 1 divided by 2. I find that interesting because this is a symmetrical formula, Planck minus 1 divided by 2, as the rest of the transformation formulas that exist within the isotropic vector matrix, as well as some of the formulas we found which equate certain number patterns, such as the 17 and the 23, revolving around the 137, and then meeting up again at the 9,384 point. Basically what I'm just pointing out is that there are a lot of interesting numerical interrelationship patterns which exist within the vector equilibriums, isotropic vector matrix. These polyhedrons get bigger and bigger. They're not maybe getting bigger, they're increasing in frequency, which is size, which might be mass, which we need to investigate at extremely high frequency measures with computers as far as I'm concerned in order to deduce maybe more exactly what's happening in the universe. Now string theory hypothesizes that at the very minutest, before any protons or even maybe before any neutrons, there's these vibrating energy strings. And I posit that Synergetics, without calling them that, has already deduced exactly how energetic vibrations or energetic strings can attach themselves in self-stabilizing intertriangulated patterns in order to create larger and larger continuums of polyhedrons. So the fractionation of these polyhedrons then giving us numerical interrelationship patterns which exist within the isotropic vector matrix and showing how they're identical to those numerical interrelationship patterns which we find within the nucleus of the atom. I'm just going to finish up here with just a couple other interesting numbers. So something else that I found interesting early on when I was doing my investigations is that string theory's equality ratio, which ratios two Chern classes and Calabi-Yau manifolds and whatnot, don't need to get into that too deeply. The first term to the second power is equal to 3 times the second churn. And so that's exactly what the cube's volumes ratio inside the isotropic vector matrix. The first volume of that first cube is 24. You bring that to the second power, you got 576. Divide that by 3, 192. That's the volume of the second cube. You take that second cube at 192 to the second power equals 36,864. You divide that by 3, you get 12,288. That's the volume of the eighth cube, or the eighth frequency cube. The 3 frequency cube then, 648 to the second power equals 419,904. Divide that by 3, you get 139,968, which is the volume of the 18 frequency cube. So any frequency cube is volume. Take it to the second power and divide by 3, and you'll have the volume of the cube, which is whatever frequency that was, like 3 to the second power is 9, times 2 is 18. So the 3 frequency volume ratios to the 18 frequency volume in accord with string theory's equality ratio. I just found that interesting. So the last thing I'd like to talk to you about is how synergetics derives the fine structure constant by understanding the ratio of its edge length compared to the 360-degree perimeter which runs along its 4 faces. If you take this tetrahedron and you just turn it up on its edge there, and you take a line through its face, a line through its another face at a 90-degree turn, another face at a 90-degree turn, and complete that 4th face. So a 360 degrees is, which is the same as the square, which runs through the central plane of the octahedron. So these ratios then take the 6,760,164 frequency tetrahedron and ratio it by dividing it by its 360-degree perimeter. And what you get is the inverse of the second root of the first 0 point of the quanta scale divided by 360 degrees gets you 0.007297475, which is very close to that fine structure constant. It only differs by 0.000000123 from CODATA's accepted number for fine structure constant. It also sets up an interesting numerical interrelationship pattern which isn't recognized currently by science, and that's that 2 times the mass of the neutron to the second power minus the mass of the electron divided by the total number of angular degrees in the tetrahedron, which is 720, is once again that same fine structure constant. And that's shown here then. 2 times the mass of the neutron to the second power minus the mass of the electron minus 720. That equals, do the inverse of the second root of Planck's constant times 10 to the 40 plus the inverse of the fine structure constant times 10 to the 3rd minus the mass of the proton divided by 360 degrees. So once again, these are very interesting numerical interrelationship patterns which I think it would be beneficial for science to take a close look at. Science may have some problem with me using 1836 instead of 1836.152 or 1838.5 instead of 1838.683 or 6.625 times 10 to the negative 34 joules compared to 6.626 times 10 to the negative 34 joules. And I think that we have to remember that what we're looking at here is a model based on an isotropic vector matrix, which basically would only exist then at 0 Kelvin where we've stopped energy movement and temperature. So taking into account the fact that the things that we're studying when we're destructuring atoms and whatnot in our Large Hadron Colliders, these things are going at high speeds with varying temperatures, and this isotropic vector matrix model may be the key to understanding things which we currently cannot understand. For instance, the ratio between the edge length of the tetrahedron compared to its perimeter. So in conclusion, I just want to say once again, the name of my book is Symmetry Prime Number Patterns in the Unified Field of Einstein. It's about 200 pages long. It's based on synergetics and Buckminster Fuller's work. Bucky felt that he had made a model of the unified field. Here's maybe a model right here of a tensegrity structure, a tensegrity icosahedron. What he felt was that this model here modeled the behavior of energy and matter along with gravity. So you have 6 compression struts representing energy or matter, and you have this embracement field which holds its structure in place. So Bucky liked to use models a lot. Regarding the transformation properties of this complex here, he said that this may come to be identified as the unified field, which, as an operationally transformable complex, is conceptualizable only in its equilibrious state. And so from that I said to myself, as I'd already done here, I want to find out what that equilibrious state of numerical interrelationship patterns shows us. So I think we have a model here showing us the nucleus of the atom. And if you're interested, my email, noel_couglin01@yahoo.com. Happy to communicate with you if you're serious about this work and it interests you. I have various other charts, and as I say, a couple hundred pages worth of information I'm happy to share with anybody that's interested in it. And yeah, you guys take care. It was nice chatting with you.